Hello, my name is EG'2021, and I'm going to present Broadmark, a testing framework for broad-phase collision detection algorithms. Together with Andrea Formico, we come from Universidade de Fortaleza, Brazil. So what's collision detection? It's the task of finding all the geometrical intersections between objects of a scene. It usually is used in physical simulations, however, it has a far wider range of applications. For instance, whenever you have dynamic objects and you need to find when they interact, collision detection can be used. At its most basic level, you have two objects and you want to find out whether they overlap or they do not. And the naive algorithm is to iterate over the triangles and try each triangle for the left object with the triangles of the right object. And this is quite slow. Instead, what you can do first is to use bounding volumes, and in constant time, you can quickly tell those objects do not overlap. So the bounding boxes themselves won't really tell you if the bunnies collide. However, it can easily tell you that they do not. And when you have a massive number of objects, it's increasingly more important to find out which pairs of objects do not overlap than the ones that do. And in the field, we call this the broad phase, which is to find which objects are likely colliding. So it's not certain, you are not certain that these objects collide, but you have greatly reduced the search space. And after the broad phase, we can do the narrow phase, which is to actually search for the collisions, finding the objects that actually collide. And given this result, we can compute their response. In other words, where should those objects go? And this is a word in itself, it's another field, and it's another different story. In this work, we will be focusing on the broad phase, which to me is the most interesting of the three, because in the end, you do have to compute the response. You can't really avoid that. You can't really not test if the objects are colliding or not. You can't bypass the narrow phase. What you can do is avoid spending unnecessary work on things that do not collide. So a different way to express what the broad phase really means is how cleverly can you decide what not to test. So to me, this is a beautiful problem, which is way more about how can you quickly find what not to do than what to do. And the most basic way to do this is just use bounding boxes and brute force the bounding boxes, which is still pretty slow, but it's way better than brute forcing triangles. However, much better than that, we can use the staple of computer graphics acceleration. We can use grids, BV8s, and KD3s. So grids are optimal when objects are uniformly distributed, BV8s are great all around, they're really good, and KD3s are not so good as BV8s, at least for collision detection. However, they pair really nicely with other techniques. And in a quick side note, those three structures are used everywhere in computer graphics. However, for the broad phase, they're used a little bit differently. So doing a little comparison, when you have ray tracing, you are testing rays against objects. So you have two sets of things that you want to test. In car-nearest neighbors, you have a query, like a region, like a certain radius of a point, and you're testing this against the objects. However, in the broad phase, it's an all versus all test. You want to see which are the neighbors, the overlaps of each object, and potentially it can be any other object. So the way the problem is framed use those structures in a very different way. Yet, collision packages usually need to support some rudimentary level of ray tracing, so it's called raycast for game developers, and some form of query testing, like which objects are in this region, which objects intersect this path. So it kind of also encodes a little bit of the other two problems. So back to broad phase, there's the sweep and prune, which is a beautiful algorithm that uses sorting to quickly find one-dimensional collisions. And this works as a pruning step. So we do only have to continue looking, we only have to narrow phase what's at least colliding in one-dimensional. And it works really well with other techniques. So if you have a KD3, you can use the sweep and prune for each cell, which is pretty nice. So, well, what do I want to go with this? So I'm lecturing about broad phase algorithms and what they can do. What's wrong with broad phase? What's wrong with the state of the art? What's there to do? You know, we have those algorithms, what's left? So let's take a look at what has been done. So these are amazing works from other authors, and they all have brought amazing contributions to the field. They have shown new ways of doing things, and of course, they've all proved that their work is a real contribution. However, you can see here that none of those authors really use the same tests. Each one of them had to create their own scenarios, their own benchmarks to access their contributions. And that's kind of an issue, because this also reflects on how people test and how people benchmark their solutions. So each one, look for different things. Everyone looks at how fast their solutions work, but they can also look at how they scale with CPU cores, how they scale with how many GPUs, how they're compared to other solutions, and so on and so forth. And the issue here is that there's no common ground. There's no a common way to do things, like a common benchmark, a common data set. And this leads to a problem that, as bitter as it is to say, the current research on broad phase is a bit unreproducible. Few authors release their source code, each work is tested on the author's own test suite, and everything is hardware dependent, so you can just take paper A and paper B, put them side by side and say this is better than this or this is better than that. You just can't, because everything was run in a different hardware, a different operating system version. And well, as a broad phase researcher or someone working in the field, what I had to do is, collect the implementations I could find, create my own benchmarks, design the scenes I would look for, and run everything myself and see how all of that goes. And I'm pretty sure I'm not the only one here in this audience that has done that. I'm pretty sure many of you can relate to this, that you once in your career had to survey the state of the art for what's open and what's available for you to use, and try to find inspiration on how to test your work, and trying to find if someone released how they did their tests, and in the end run everything yourself. And it would be so much easier. It would have spared me like 6 months to 1 year of development if there were more open implementations, there were a common set of benchmarks, and all of this was really accessible for anyone to run. In other words, if the research was more reproducible, it was more open. And this is a thing we all should strive for in our fields. And if there is one takeaway from this presentation that I would love if anyone watching this would give it a thought, is your field open? Is there a common benchmark? Can there be an open benchmark? It's also an important question. And how difficult it is for someone new to start doing research on it? And if you have gone through all this trouble to assemble the baselines, to create the benchmarks, and run things yourself, why don't you release that? Why don't you, give this to the world and see how it goes and see what people do? And in my case, that's exactly what I've done with Broadphase, which is something that I deeply love, and I would love to see more people seeing the beauty of those algorithms and seeing what the field has. And that's this work. That's Broadmark. It's an open implementation of algorithms, of benchmarks, and all made really accessible, made really extensible, so that people can make it bigger, add more tests, add more algorithms, measure different things, but in the end, contribute to the broad phase field. And we've did an extensive survey of what really people are testing in each one of those papers, and we've created scenarios that can stress all of those things. We can do uniform and non-uniform distributions, which is common for people that are doing grids. We can do dynamic and static scenes, which is a major component of broad phase design, and can also simulate simple versus complex objects. And there are benchmarks, there's baselines for what's the best serial solutions there are, which are parallel solutions, GPU solutions from Bullet, and those come from the academia. Some are from papers, some are from Bullet, some are from Seagull, and it's an open collection. It's 13 algorithms And it's funny because since there were no Broadmark before, we don't have also a comparative study, like a large comparative study of how those algorithms perform. And there's just local information, like those hearing this work, those hearing this work, and there's no comprehensive summary. And with Broadmark, we've released it under GitHub, so anyone can use it, anyone can check and redo all of the tests that I've done. So at this moment, I would like to speak a little bit more of what Broadmark is and the decisions that we've taken when designing it, and also a little bit of this comparative study on what's there in the field and which performs best when. So at a major level, Broadmark is based on two components. One's based on Unity, and it's based on creating the scenes themselves, so going from up to 1 million objects, and those are baked to a file, which we call the simulation file. It's .aabds, which is a very important step because you don't really want to do 1 million rigid body simulations over and over. You want to do them just once and run it again for each algorithm. And this is really okay because the algorithms are correct. So if you give them the same input, they should give the same output, maybe just in a different order, but it's the same output. So we can just record the simulations done with one of the algorithms and just feed it to the other. And that's way faster. And well, given those simulations, there's the Broadmark itself, which is a C++ implementation, that collects the algorithms, give them the simulation, and measures the results. Here are the three main themes of Broadmark, which is Brownian, which is kind of the de facto standard testing scenario, which basically every paper has something analogous to Brownian, a uniform and dynamic scenes. Freefall, which is a very static scene with objects laying on the ground, which is also really common, and Gravity, which is an extremely dynamic scenario and was designed to force a large number of collisions. So it's really pushing the algorithms to their maximum. And a very important decision that we took was parametric scenes. So we try to have a constant object density, because so whenever you increase the number of objects, you get more or less the same simulation. And this is very important because first here in the middle, you can see a 1,000 objects simulation, which has a density of 1%. So if we scale it to 32,000 and we don't have like this constant density, you get the result from the left, which is horrible because, if you really do this, grid algorithms will just, scale much better because in reality, you are getting a uniformly distributed scene on all three axes because the space you have is just filling up with objects. But if you have the constant density, then you actually can scale from 1,000 objects to 1 million and still have the same properties, the same density, the same distribution, and that's very important. So here's a screenshot of a wizard that generates the simulations. They're all baked to files. And the Broadmark core that I was talking about is a minimal C++ implementation. It has the scenario reader, the broad phase interface, time and pruning measurements, and preframe results. And there's also a set of Python scripts that you can use to run tests in batch and also to plot the results. And regarding implementations, we have 13 families. We talk families because you have like brute force parallel, brute force AVX, brute force parallel AVX, and so on. So there's brute force, sweep and prune, grids with SAP, there's axis sweep, DBVT from Bullet, there's Seagull from Seagull, Tracy by Tracy, and KD3 by us, which is our prior work, and 3 GPU implementations by Bullet. So this KD3 implementation is based on that idea I've spoken before of having a KD3 and the sweep and prune, and was also published in Computer Graphics Forum. So talking a little bit about results, here it's more or less how I'm going to present them. So we are capping the results to half a second, stretching our analysis to 1 million objects, and we are going to see serial algorithms first, then parallel algorithms. So here's Brownian with serial solutions, which is the uniform and dynamic scene, and you can clearly tell that basic approaches like BF and SAP are, not really good. Static optimized solutions also not, and dynamic optimized solutions are way better because it's a dynamic environment. And you know that's our prior work here, and that's a grid-based solution here. So it kind of shows off how grids work really well on those uniform distributions. And when we go to parallel, we can see that GPU works really well, and the parallel grid approach is also way better in the parallel settings, and especially compared to the best serial solution, which is scatter tree. And however, you can see that there's not much of a difference. GPUs are just 4 times better than the best serial solution, which is, well, you would expect like 80 times better. So that shows a little bit how the GPU and multi-core algorithms of broad-phase are not really well developed at the moment. So here's freefall, which are static scenes. So we have the opposite here. Dynamic optimized solutions are way worse than static optimized, and KD3 also works really well. When we go to the parallel domain, we see that the parallel solutions really just don't improve that much from staticness, while the GPUs perform roughly the same than when the Brownian scene, here the GPU solutions in red, but the best serial solution still works better than the GPU. So that's one thing CPU works really well. It's when you have a few objects moving. And gravity, which is like the stress test, really shows here because everyone is worse. Everyone is going really bad. And when we go to the parallel solutions, we can see that serial and multi-core are kind of the same, and GPUs are doing pretty well. So taking a wider view of this, we can see that the best CPU solution are not really far off from what's the GPUs algorithms we have or the multi-core algorithms we have. So that shows that broad-phase is really well developed for single thread, but there's way more work to be done on the multi-core and GPU side. And that's really not apparent on the previous literature. You just would see algorithms being like 80 times and 90 times better. But when you actually put them all together with modern implementations, not old baselines, there's not much of a difference. And the GPU, and it's not designed to work well, equally well on all 3 scenes. However, it's just so strong, so powerful, so arithmetic powerful that it just works really well on all 3 scenes. And that's something that could be exploited in further work. So concluding, this work contributes Broadmark to the collision detection field. It's an in-depth review of modern techniques. It's a set of open implementations and benchmark problems. And using Broadmark, we've conducted the largest comparative study of the recent literature, showing serial, parallel, and GPU solutions, both from industry and literature. And we found that GPU algorithms are the fastest, which is kind of expected, but not by much. So unless in extremely dynamic scenes, which is the case of gravity, GPU performance is within 2 to 4 times the best serial solution. And CPU approaches are really good at handling static scenes, which is something that they just can explore much better than GPUs. And the best serial solution often outperforms multi-core approaches. So what we can take from this is that high-end parallel approaches do not really scale well with hardware, and scaling is even harder on static scenes. Finally, as future works, we would love to explore potential avenues such as improved GPU usage, mixed CPU and GPU algorithms, so trying to use the CPU when there's less objects moving and the GPU when we have more dynamicness, and a better scaling of CPU algorithms to both threads and SMID lanes, and general solutions that work well on all 3 scenes. And also to continually improve Broadmark based both on its own evolution and on feedback. So thank you.